Alright, so we're picking up where we left off. This is part 2 of ignition coils. If you want to see part 1, you can check the description. But this is the pulse width modulation square wave we made. 47 Hertz, 11% positive duty cycle. It's intended to be able to drive this ignition coil indefinitely without overheating it. We made the waveform using this 555 timer, some resistors, a capacitor, and a transistor. All the details in part 1, but we have it all hooked up to the 12 volt power supply. We're going to run it and see what it can do here, but one important note is that if it's actually installed in a vehicle, the waveform will not just be like this. It's completely RPM dependent. So at a faster RPM, you need a different waveform. So it's much more complicated. But we have a nice simple waveform that we can drive this thing indefinitely for bench testing and experimenting. So we're going to run this thing for a minute to see what it can do, and then in the rest of the video, we're going to implement it into a casing. Yeah, and with that being said, we're just going to get some nice footage here because that's what it's all about. So we're just going to see what this thing does. I'm going to flip this switch. You can see when I move it further away, it's louder. If I move it very close, it gets very quiet. I don't really know why, but if you move it too far away, instead of making an arc, it just arcs across its own windings and causes damage. So we don't want to push it too far. Either way, we're going to build this thing into a nice casing so that it's a lot easier to experiment with. And that will all be in the next section. Alright, before we build it into a permanent casing, there's just one thing we have to do, which is test the air gap. We want as big as an air gap as we can get, because you want a big arc. But if it's too big, instead of arcing across the air gap, it's going to arc inside the internal windings and cause damage to the insulation. So we're going to start at a small air gap, slowly move it further and further, until we see the threshold where it stops. And then we're going to move it just back a little bit to where it's firing consistently. And we're going to take a measurement on the length. So I'm going to turn it on. Starting at a small gap. Slowly go out. Getting louder. So when we get here, it stops being consistent, so we'll move it back in. So that's a good consistent firing point right there. So we're going to try and get a good measurement here. So we'll get our measuring tape like so. Sorry, it was a bit blurry. So we get about 7/8 of an inch. For an engineering window of safety, we're probably going to go to 3/4 inches as a permanent setup. And that should be an adequate air gap for the final casing. So like 3/4 of an inch so that it can fire consistently without damaging the insulation in the windings. And so we've decided for a case, we're going to use this. This is a motor assembly from a cheap stick vacuum. I got it at the thrift store. It's good. It's got a handle. It's got a switch. It has a cord for now, but eventually we're going to have this thing battery powered. But we're going to leave the cord in for now just to hook up our DC power supply to, because we don't have a battery yet. So we're going to see if we can get this thing to fit in there, and then it'll shoot out that end when you flip the switch. So we're going to open this thing up and see how much room we get. All right, so we opened up the case. Just take out the screws. It comes right in half. This is what's inside the original vacuum, just as a quick checkout. It's got a little suction motor and a switch, and that's literally the entire circuit. It's a very simple device. It's a 120 volt AC motor. We have it hooked up to 32 volts DC because it's a universal motor. It runs on DC and AC. That's thanks to the windings as opposed to using permanent magnets. But yeah, you flip the switch, turns on, you get about 32 volts, 1 amp, so that's about 32 watts DC. But we don't really need that, so we're going to take it out, save it for later. We're going to keep the switch and see if we can get this coil to fit inside. Yeah, so it's a little tight, but I think we can make it work. We're going to just have to cut away some of these plastic walls on the inside and cut a little hole for the end to stick out of. And I think we should be able to get it so that it closes nicely. So we cut a bit of the plastic out of the inside, put the coil in there, closed it up, and as we can see, it's pretty good. It's going to work nicely. The switch is right here, it's just not installed right now. We just have to make another hole for the other electrode to come out, and then maybe we can test it out. Alright, change of frame here, but we kind of made a discovery. So we were in the process of taking apart the ignition coil. You can see this one's missing the stem. This is the original layout. Inside the middle of the stem, we found this little guy. Wasn't sure what it was. I put an ohm meter on it. It's a 1800 ohm resistor, so it's 1.8 kilo ohms, and it goes in series with the high voltage output where the spark happens. And we found something quite interesting. When we remove this resistor, like as we have done in this coil, and when we fire up our spark here, first of all, it's brighter. I don't know if you'll be able to tell, but I can't say that it got noticeably longer. But the interesting thing is, when you do it like so, it actually causes interference on my television. So I'm going to try and capture all of this. So that's very interesting. You can see it's creating interference with my television. Nothing happens on my laptop, so I guess it's either a better design or just taking it in a different way, I guess. But the interesting thing is when you put on the resistor, I'll do that right now. All right, so you can see I've put the resistor in series with the output as intended. And now we can see when we make the spark again, nothing is happening on the television. So I thought that was kind of interesting. Can't decide if I want to leave the resistor in the final product or not, but I feel like it's cooler to have it out because then it causes interference with stuff and the spark is noticeably brighter. But we'll just carry on anyways. Thought that was cool. Alright, with that being said, back to the mechanics. So we've got our grounding electrode mounted in there. So this is kind of the output stage that we're going to have the arc coming out of. But now we kind of go to the challenging part and seeing if we can get all the circuitry to fit inside as well. Because right now it's just all mechanical and we don't have anything electrical hooked up. So we're going to have to build the circuit on a little permanent board and tuck it in there. And then we can give it a test run. Alright, so I'm going to show you where we are so far. On the right we have our device. We have the cord coming in. That's here on the diagram. That will be connected to 12 volts DC on the outside of the cord. Because for now we don't have a battery, so we're just going to hook up the 12 volts to the end of the extension until we get a battery. We have the positive going to the switch that's right here, coming out of the cord. This white wire coming out goes to a splice. That's this one in red. This splice goes to the ignition coil. As you can see, the red wire. But it also has to go to the board that we're going to make. We have the ground wire coming in, the negative. It goes to the ignition coil negative. That would be this splice. You can also see that it has to go to the negative electrode for the spark gap. That's this screw. So there's 3 wires going into there for now. And we have our signal wire for the coil out on its own, right here. And that will be the 3rd splice there. So all we have to do is make the board, make 3 wires coming out of it, 1 for positive, 1 for negative, 1 for the signal output. I can tuck it in there, hook it up to the 3 splices, and this thing should be ready to go. Okay, so this is what we made. I know it looks really bad, but it actually works quite well. We have our board here with our components. I know the capacitor is way oversized. I know the transistor is way oversized, but it's just all the components that I had with me. So we have our red output, which is the PWM output of the timer. We have our white, which connects to ground, and our black, which connects to positive. We'll tuck those down in here, hook them up to the 3 splices, and we're going to run it and see how it works. But it's based on these 2 diagrams from the previous video. We have our timing circuit with the positive connection and negative connection also goes there. We decided not to use this capacitor. We have our output. The output goes here to the base of the transistor and inverts the signal for the coil. So we're going to hook it up and watch it in action. So we've made our splice connections. We've tucked the board just down underneath the coil stem there. You can see the giant capacitor. And yeah, we're just going to close it up and take it for a spin. So this is the completed device. It's fully functional. Just one thing. We had it hooked up to our 12 volt DC power supply, variable, 0 to 32 volts. But we actually completely destroyed the power supply in the process. As you can see, it's just flickering. You can see the voltage changes when you move the knob, but no matter what I do, I just can't get it to supply any power. So maybe in the future, we're gonna do a video exploring that. But the long and the short is, we had the arc going off of like a ruler, a metal one, sticking off the top. And I think the arc went through the machine and damaged a component. So in the future, we might diagnose that. But in the meantime, we have a car battery, because who doesn't have a car battery? So we got the red wire positive, black negative. They go here, red wire positive, green wire negative. So this is the cord going into our device. As we said, we do not have a battery. We might get one in the future to make a completely portable taser, but you can see it's fully functional. You flip the switch. And I'm just going to say one thing, you do not want to touch that. That's brutal damage right there. But yeah, it's a really nice device. I'm proud of it. The casing is really nice. It's a pretty professional product. It's only a little bit dangerous, so I recommend don't make your own one unless you know what you're doing, but I'm pretty happy with it. All you have to do is hook up the cord to 12 volts, turn it on, and you get a super high voltage arc on the output. A nice little taser. But yeah, we don't have much time in the video, so yeah, rest in peace, power supply. Like the video, subscribe to the channel, just because that costed a lot of money and now it's gone. But yeah, in the future we're gonna do more experiments. Cool, dude.